be working with an implicit derivative in this video, and we're going to be trying to find the second derivative of this implicit equation. So the first thing we have to remember is that the derivative of e to the anything is that e to your exponent times the derivative of my exponent. So the derivative of 3y is 3, but because I differentiated with y, I'm going to have to put dy dx. The derivative of x is 1. I don't need to write dy dx. So what we want to do at this point is we want to move the 1 over here, and I want to move that 3 dy dx over here. So I'm going to get e 3 dy dx times e to the 3y. I move the 1 over, and then I move that 3 dy dx over, equals that negative 1. So then I'm going to factor out the dy dx, because that's what I'm wanting to solve for. And I'm going to get 3e to the 3y minus 3 equals negative 1. I'm going to divide both sides, and I get that my first derivative is going to be negative 1 divided by 3e to the 3y minus 3. Now, there are a couple of ways that you might want to do this. Some people might do a quotient rule. I am not a fan of the quotient rule. I think we've talked about this. So I would actually differentiate this as negative 3e to the 3y minus 3 raised to the negative 1. You could definitely do a quotient rule, but I'm going to prefer doing a chain rule so that I can then do that. So when I do that expression, get some space on my screen here. To work the chain rule, we're going to work from the outside in. So I'm going to have negative 1 times a negative, which is going to be a positive 1. Then I'm going to have 3e to the 3y minus 3 raised to the negative 2, because negative 1 minus 1 is negative 2. Then I'm going to multiply by the derivative of the inside. So the derivative of 3e to the 3y is 9 dy dx times e to the 3y, because I'm taking the derivative of e to the 3y, and then I'm taking that. And then we have minus the derivative of 3, which is going to be 0. So then I'm solving for the dy dx here, which is unique because it's the second derivative. I am actually going to plug in dy dx for the original equation there, okay? So this would become 3e to the 3y minus 3 to the negative 2 times 9. I'm going to replace dy dx with that derivative, and then I'm still going to have that e to the 3y. So what am I going to do here? I'm going to take my positive values and put those here in the fraction over, I have this 3e to the 3y minus 3 to the negative 2 times the same thing to the negative 1. So I'm going to add those exponents, and that's going to be negative 3. So when I take 3e to the 3y minus 3 to the negative 3, to write that as a finalized fraction, it has to go in the bottom, and we still have this negative hanging out. So I'm going to have this in the bottom. So the questions I've been getting about why this has a cube in the bottom has to do with this step, with taking that dy dx and replacing it with the original. Now the lab does sometimes prefer to switch this around and get rid of the negative, but it will take the negative in front as an answer. So it will take either form of this, either the negative here or swapping this around as 3 minus 3e to the 3y to get rid of the negative. So the key is remembering on the implicit second derivative, you have to replace dy dx with what you got from this step. And then you're going to use a lot of algebra to really simplify that.